Hello, in our lecture today we will discuss how does a transistor work. We will focus on MOSFETs. MOSFET stands for metal oxide semiconductor field effect transistor. Before starting lecture, let me introduce myself. I am Dr. Imran Khan and I am holding PhD degree in electrical engineering. My area of specialization is digital analog CMOS integrated circuit design, device transistor modeling for future generation CMOS. As you know that MOSFET is a basic building block of our digital integrated circuits. Nowadays, integrated circuits have billions of transistors inside small silicon area. MOSFETs are used extensively in integrated circuits due to its characteristics like small size, high gain, and power characteristics. So, MOSFET MOSFET stands for metal oxide semiconductor field effect transistor. MOSFET has two types: N-channel MOSFET, NMOS, and P-channel MOSFET, PMOS. So in this figure, we will discuss an NMOS transistor. So here you can see it's NMOS transistor. So you can see in the red it's polysilicon. It is called gate. So while in the green you can see these two N plus diffusions. So these are source and the drain. You apply voltage at the gate and the drain and controls the current between source and drain. Because this is NMOS transistor, source and drain terminals, they have N plus diffusions, while its body is P type. Similarly, you can construct a P channel MOSFET if you place here P plus diffusion here and N type body here. So you can easily convert this into PMOS transistor. How transistor work? In this slide we will discuss how transistor works. Here in the red you can see the gate terminal, in the green its source and the drain. So this gate is connected to this channel via an insulator. This insulator is called silicon oxide, SiO2. Input gate current to the MOSFET is always zero because the gate is connected to this channel via an insulator. So there is no gate current to the MOSFET. So its Ig is always zero. So you apply voltage at the gate terminal and the drain terminal, and you control the current between the source and the drain. So this is the basic operation of the MOSFET. So in our next slide we will discuss about the process of channel formation and how does the current flows between the two terminals of the MOSFET, source and the drain terminal. So in this slide you can see simplest MOSFET structure. VG is the gate voltage, Vs is the source voltage, and Vd is the drain voltage. So we are discussing N-channel MOSFET. So its body is P-type substrate. So In this slide, we will discuss how you can form a channel between source and drain and how current flows between source and drain. When you apply a gate voltage, positive gate voltage will create negatively charged region depleted of positively charged holes in the semiconductor underneath the insulator. So here you can see when you apply this positive gate voltage, you can see the region here, negatively charged region here. Increasing the gate voltage will force the depletion layer to go deeper. So here you can see if you increase Vg, the depletion layer will go more deeper. Here you can see the scenario. Increasing the gate voltage beyond the threshold voltage Vt will make electrons appear at the semiconductor surface. So here you can see some electrons on the semiconductor surface. More electrons appear at silicon oxide interface as VGS is increased. So here you increase more VGS and the electrons, you can see more electrons on this surface. A conductive N channel is created between source and drain. So here you can see that this channel is created, but still current will not flow. So how does a current can flow between source and drain? This we will discuss. So you already applied Vg. Your Vg should be greater than Vt, and for current flow you also have to apply this Vd, this drain voltage. When you apply this Vd greater than 0, lateral field moves electrons from source to drain. So here you can see this is how the current will flow between source to drain. Regions of operations of MOSFET. We know that MOSFETs have three regions of operation: cutoff region, linear or triode region, and the saturation region. So here we will discuss about these three regions and the equations of ID and currents. First of all, we will discuss the operation in cutoff region. When your Vg is lesser than Vt and VGS is 0, then there is no current. ID is 0. This is called cutoff region. Linear region. So here you can see this is the MOSFET structure in the linear region. So here you can see a channel. So this device is in linear region. You have applied this VGS and the VDS. To achieve the linear region, your VG should be greater than VT, and VDS should be lesser than equal to VGS minus VT. So when you apply these conditions, you will see your device will behave in linear or triode region. So here is the equation of ID in the linear or triode region, where Kn prime is cross transconductance parameter and Kn prime is equal to mu n C naught x is equal to mu n E naught x by T naught x, where mu n is electron mobility, C naught x is oxide capacitance. So C naught x is equal to epsilon naught x divided by T naught x. This is epsilon naught x is oxide permittivity and T naught x is oxide thickness. Transistor operation in saturation region. If you keep on applying this VDS, when your VDS is greater than equal to VGS minus VT, you can see here the channel pinch off. Here it is channel pinch off. This is called the saturation region. In the saturation region, constant current flows. So for the saturation region, your VDS should be greater than equal to VGS minus VT, and here you can see the ID equation of ID in the saturation region, where this lambda is the channel length modulation. So this was the basic operation of MOS transistor. So if you have any question, please don't hesitate to contact me. Thank you very much for today. See you next time.